This is the first of several videos on thermodynamics, and since this is a new topic, we have to introduce terms and define terms. Thermodynamics is the study of energy changes and energy transfer. Thermodynamics determines if a reaction can take place. It does not determine how fast a reaction will occur. That is determined by kinetics. There are two terms utilized in thermodynamics that are frequently confused, and those are heat and temperature. And heat is not the same thing as temperature, though temperature can reflect the amount of heat. Heat is the amount of thermal energy which is transferred from a hotter substance to a cooler substance. Temperature is a measurement of molecular movement. Heat always goes from the higher energy substance to the lower energy substance. The unit of heat in the metric system is the joule or the kilojoule. And since this is the metric system, 1,000 joules equals 1 kilojoule. This conversion needs to be automatic, as we will be going back and forth quite frequently. There are 4 laws of thermodynamics: the zeroth, the first, the second, and the third. The zeroth law of thermodynamics states if a system A is in thermodynamic equilibrium with system B, and system B is in thermodynamic equilibrium with system C, then system A is in thermodynamic equilibrium with system C. This is really a version of A equals B and B equals C, then A equals C. It's called the zeroth law because it was elucidated after the first and second laws had been discovered, but is felt to be even more fundamental, and so it should precede the first and second law, so it was designated the zeroth law. The first law of thermodynamics states energy can be neither created nor destroyed. It can only be converted from one form to another. This is also called the law of conservation of energy, or the second fact of life. The second law of thermodynamics states that the entropy of a closed system will increase for an irreversible process and remain unchanged for a reversible process. The energy of part of a system can be decreased, but that involves the input of energy, and thus the system is not a closed system. We will talk more about entropy several videos down the line. The third law of thermodynamics states, at absolute zero, the entropy of a pure crystalline substance is zero, and that's all we'll say about that. On to some definitions. The triangle is known as delta or change. It's the Greek letter D. In science, this is calculated as the final value minus the initial value. It's okay if it's negative. X sub f minus x sub I. A state function is a change in a quantity which only depends upon the final and the initial values. How the change occurred doesn't matter. An example, let's take the track. We go down and I mark a spot with the yellow line and then a spot with the black line. I call the yellow line 0 meters and the black line is 50 meters away. You then run almost a complete lap. You start at the 50-meter line and run till you hit the 0-meter line. Displacement is the distance between where you started and where you finished in a straight line. The change in displacement is the final distance minus the initial distance. Here, the final distance is the 0-meter mark, and the initial was the 50-meter mark. So 0 minus 50 is your change in displacement. You have been displaced minus 50 meters. Your distance, the track is 400 meters. You ran all the way around the track except for the last 50 meters. So your total is 350 meters. Let's do it again, but this time you're going to run almost 2 laps. For your displacement, once again, it's final minus initial. You started at the 50-meter mark. You finished at the 0-meter mark. So your displacement is once again minus 50 meters. The distance was 800 meters, would be 2 laps, but you left out 50 meters. So your distance is now 750 meters. The change in displacement, the delta D, is minus 50 in both instances. This is a state function. The distance traveled was not the same, so therefore distance is not a state function. If you ran 500 laps and started at the 50-meter mark and ended at the 0-meter mark, your displacement would still be minus 50 meters. We will be talking about the system. The system is what is being studied. It is determined by the observer. The surroundings are defined as everything that is not the system. The universe is the system plus the surroundings. We will be limiting the surroundings, so we will be limiting the universe. Heat is the amount of thermal energy which is transferred from a hotter to a colder object. Enthalpy, or H, is the total heat content of a system. Now, we can't measure that value, but we can measure the change in H, or the delta H, and delta H is a state function. Entropy, which we will come back to later, is the number of microstates a system has. The more possible microstates, the higher the entropy. Entropy is also a state function, so delta S is the final entropy minus the initial entropy. And as I said, we will come back to this at a later time. Now, the next two definitions are dependent upon what is defined as the system. The first is exothermic. In an exothermic process, the system loses energy or heat. The delta H for the system will be negative. In an endothermic process, the system gains energy or heat, and the delta H for the system is positive. If you look at a reaction profile for an exothermic process, you see that the H of the product is less than the H of the reactant, which means that heat is released because you now have less of it. Delta H must be negative because you are subtracting a larger number from a smaller number. Examples of exothermic processes are making bonds and increasing intermolecular forces. As expected for an endothermic energy profile, the product heat is greater than the H of the reactant, which means that heat must be absorbed. The delta H must be positive because you're now subtracting a smaller number from a larger number. And examples of this are breaking bonds and breaking intermolecular forces. Now, there is a relationship of the delta H between both the system and the surroundings. And this can be stated as equal but opposite, or delta H of the system is equal to the negative of the delta H of the surroundings. The heat lost or gained by the system must be gained or lost by the surroundings. This is just another way of stating the first law of thermodynamics. Energy cannot be created nor destroyed. It can only be transferred or changed. So that's the introduction to thermodynamics. To review the highlights, Thermo studies the transfer and change of energy. It can determine if a reaction can take place, but now how fast the reaction can occur. Heat is a measurement of thermal energy, which is transferred from a higher to a lower substance, while temperature is a measurement of particle movement. In the first law of thermodynamics, energy can neither be created nor destroyed, but it can be converted from one form of energy to another form. This is known as the law of conservation of energy, or the second fact of life. Heat has the symbol Q, enthalpy has the symbol H. We will tend to use the two symbols interchangeably, and we will almost always use the H. Can't measure H, but we can measure the delta H. Delta H is a state function. State functions only dependent upon initial values and final values. It's not how you get to the final value. It's always final minus initial. You determine what is the system. Everything else is the surroundings. If the system loses energy or gives off heat, it is exothermic, and the delta H will be negative. You have an endothermic system when the system gains heat, and the delta H will be positive. Remember, the heat change between system and surroundings is equal but opposite, otherwise known as delta H of the system is equal to minus the delta H of the surroundings. This is just a restating of the first law of thermodynamics. In the next video, we're going to show how delta H is a stoichiometric value.